Okay, here we are. It's the physics video lecture once again. Fluid mechanics video lecture 4. And we're doing some thermo and vector analysis review today. But I'll begin with our sets of equations, first of all. And then we'll continue the discussion. So yeah, we have from conservation of mass, the continuity equation, divergence of rho v equals 0. So conservation of mass. Then we have from Newton's law, acceleration of v dot gradient applied to v minus 1 over rho gradient of the pressure. We'll go ahead and put g in here, and of course g can be absorbed into the pressure if need be for a simple form. And then we had constant entropy density plus v dot gradient fs is equal to 0. So good, this was Newton. And I'll just write here entropy. So we have a bunch of vector expressions that we've already had to deal with. And then we have these thermodynamic quantities. So on the one hand, we have vectors, vector field, plural, well, I'll just write vector field. And on the other hand, we have these thermodynamic quantities, and we can just list what we have here: density, pressure, entropy. Other things could be there as well: temperature, etc. Okay. So what we've done so far is we've done the case where the divergence of the velocity field vanishes, and then these things simplify nicely. And I'll just write here, thus far, divergence of v equals 0. We were able to talk about hydrostatics and a couple of interesting applications. And then we had the rotating bucket example. So we did have some fluid flows, namely the rotating bucket. It's a good one to take right at the beginning, because in addition to just giving an interesting result, it introduces us to the necessity of talking about curls and things like that. Okay. We have the rotating bucket. Yeah, we also had I'm just going to call it the bathtub vortex. So yeah, we saw there that we needed some interesting vector analytical properties. So yeah, we need a vector review, and we need thermodynamics review, or just a little information on that and how we're going to deal with these quantities. So that's what we're going to do next. Now the full review in the way that you would do it for, say, a beginning electricity and magnetism course, you're doing a classical field theory, you can spend a whole week or two on these things. And I want to just compress it without any cheating into 1 hour, basically. 1 hour, maybe a little bit more. So what we'll do is we'll start with the vectors, and I'll give you my outline. You'll have the whole concept, and we'll fill in as much as we need, okay? So first of all, with vectors, if we were going to take it from the top, we begin with, in fact, I'm going to number these things. That way, you can leave as much room in between these as you want. You can fill in as you see fit. So if we're going to take it from the top, we would just first talk about scalars and vectors, and then we define the scalar product and the vector product. So scalars, vectors, vector algebra, this would all be review. Scalar, vectors, vector algebra, and then we talk about the scalar product and the vector product. We'd probably be in Cartesian coordinates. And then we would introduce triple products. And these are the types of things you should have done at least once in your life, actually demonstrated all these things. So the triple products I'm talking about would be A dot B cross C. You guys remember it's the volume of a parallelepiped, and therefore you can just cyclically go through these. So C dot A cross B, and then B dot C cross A. That's one of the triple products. And the other one that we would do would be A cross B cross C. And these things just come up in applications. Okay? And ideally, we've demonstrated and done the proof for everything we ever ran across. So then you would do B A dot C minus C A dot B. And right here you have, you're turning these three, since you have a dot product, into a scalar. Here you have all cross products, so the result is a vector. Okay. So good, if you've never done these proofs, you can do them. Typically with these types of things, with the cross products, if you get one component, you're good to go, okay? Because then they work cyclically. Good. So then on our list, we would talk about differentiation. So I'm going to keep my numbering scheme here. So 3, we would do differentiation. And we have, say, the time derivative of a vector. What does that mean? Or we could start with the time derivative of some scalar x, y, z, and t. We did a couple of these already. And then you have to know the chain rule. Very important, the multivariable chain rule. And that, we'll go ahead and do the time derivative first. But then when you have the chain rule here, you're looking at df, dx, dx, dt, and the same for y and z. Y dt plus df, dz, dz, dt. Okay, and this will turn into, you'll recognize that you've got a scalar product that you introduced over there, and then you can define the first part of your scalar product as the gradient of f, and it's dotted here into the velocity, dx dt, dy dt, dc dt. So that's one example. Or we could put dr dt here. maybe better for the moment. d over dt, like that. So yes, here differentiation. For a vector, you would then say, okay, I have this, I have to do it 3 times. And so important is the multivariable chain rule. Interesting to go back and see the proof of the multivariable chain rule. You actually have to go all the way back to the definition of the, kind of the generalized definition of the derivative as a linear mapping. So, but anyway, so you're back to the multivariable chain rule. And I'm numbering things still. At this point, 3, 4, we already introduced the gradient, so you introduce those basic operators, gradient, divergence, and curl. And you can leave space if you want to actually put their definitions there. I'm just assuming we have them in Cartesian coordinates. But you know, you identified this thing here and defined it, and then the other 2 are going to come into place as well. So now we can put together a big list of I'm just going to call them product rules. So derivatives, product rules. And I'm just going to write out this list. And you guys can prove as many of these as you'd wish, as you'd like to. Some of you probably say, we've already done that. But once you have them there, then you can use them, and they come in handy. So what do I mean by product rules? I'm just going to break out with the entire list I have here. So here we're still under 5, and we have, I already gave those triple products, so good. Gradient of fg, that's the simplest one. Gradient fg plus f gradient g. Gradient of a dot b. So these are a lot longer. A cross B cross C. Not so fast. I'm just going to concentrate on copying these things down. So gradient of A dot B, A cross curl of B plus B cross curl of A, it's got to be symmetric, plus A dot gradient B plus B dot gradient A, right? This is one of the operators that came up in our Euler equation, for instance. Okay. So that's the gradient A dot B. The divergence of scalar times a vector is equal to F divergence of A plus A dot gradient of F. The divergence of A cross B is equal to B dot curl of A minus A dot curl of B. So yeah, you can try these to your heart's content. This one we're going to use a number of these. Cross B, curl of F A is equal to F curl of A plus minus A cross A dot A cross grad F. Grad F. And I'm going to 1, 2, 3, 4, 5. Continuing, we have curl of A cross B equals B dot grad A minus A dot grad B plus A divergence of B minus B divergence of A. And finally, so these are all actually all pretty important. Very important here is curl of vector equals the gradient times the divergence of a vector minus del squared of that vector. So we'll make use of all of these. Should I number them? Probably doesn't matter, but here we go. Actually, 5, 6, and 7. So after these, there are two really basic properties that will round out the entire set here. The 8th one is that the divergence of a curl identically vanishes, and the 9th one is that the curl of a gradient identically vanishes. Good, so these, and you find them on maybe the inside cover of Griffiths or Jackson or somewhere, and we'll make use of a number of these. So especially if you've demonstrated these calculations before, then you feel like you own them. These, of course, are very fundamental. Divergence of a curl of a gradient vanishing. But these have all kinds of uses. So after you've done differentiation, define these things, and then you can just go to town and get all of these product rules. So that was point 5 on my list here. And now I'm ready to go to integration. Let's see here how we're doing time-wise. Okay, great. So I'll just put a note here. Examples have already been brought to a fair number of examples in the first lectures. So we have examples of these expressions, for example, in our Euler equations, and that kind of tells us that we're going to be using these to transform the Euler equations later on to some other convenient form. Okay. These we're going to use a lot when we start talking about integral theorems, which is next. So after going through all of this vector algebra and vector differentiation and product rules, we'll talk now about integration. So I'm going to keep my numbering up. This was 5. Okay, so for integration, I really want to talk about the fundamental theorem of calculus and then some generalizations and corollaries. So we're numbering things here, 6. We would talk about integration. And all of these things are fun to prove or give rudimentary proofs of. We're going to move a little faster than that. But we'll start with the fundamental theorem of calculus. Integral f prime of x a to b is equal to f of b minus f of a, which we always use. And now we want to talk about the integral theorems, how this works in higher dimensions. So, this is just a function, and we know its interpretation as the area under the curve. Okay. But suppose we go from here to a line integral. So line integral is next. And here we would have something like this. Integral gradient of f dotted into dl, and I'll just say along some curve that goes from A to B, where A and B are points in space. That is going to be f of b minus f of a, evaluate f at those points. And the proof of this actually goes directly back to this when it's adequately defined. Okay. So yeah, we've got the line integral. So that's this basic integral theorem. So integration here, this is the basic integral theorem. Okay. So we've got the line integral. And then next we go to surfaces. And then we're looking at Stokes' theorem. And the pattern is it's the integral over the derivative equals the values at the boundary. So if you're now doing a surface integral, you've got curl of a vector field f dotted into a surface normal d area. And that would be a surface area, I'll just call it A. Well, now this is the derivative, so we go from a surface integral to a line integral, and then we would say we've got the boundary of a closed oriented integral of this f dot dl, properly defined. These can be demonstrated pretty nicely with just a two-dimensional grid. So if you try to do this in the xy plane, so let's try to do it on a smooth curve in the xy plane as opposed to a more general curve, and you break this up into a raster, then you can do a rough proof of that. You possibly have seen it before. So you've got your surface integral, and then next you've got the volume. And for the volume integral, we've got our derivative. It's the divergence of some vector field over the volume. All right, D capital V. And here's the volume. And then you go down one dimension, and so this is the surface integral f dot n hat d surface along the boundary, the surface that bounds that volume, right? That's Gauss's integral theorem. You recognize them all as being a version of this. So we've already made use of this type of discussion. We were talking about vortices and the curl of that rotating bucket. So yeah, these play a big role in fluid mechanics and in field theory generally. Okay, so in classical field. So what comes next on our list here? Well, you know, since in my list I called this 7, so I'm going to call this 7. Okay, next on our list is integration by parts. I'm going to make use of one of these that I just erased here. So we do integration by parts. I'll number this 8. And we're going to just take our fundamental theorem here and start with a d dx of f and g equals f prime g plus f g prime. We integrate both sides. Equals integral f prime g, we'll do a dx here, dx plus integral f g prime dx. So that's just an identity. And now we just decide which one we're going to take. Here we will have which one we're going to take as our boundary. Just to make sure I stick with my concept here. Yeah, this should just be standard form. Yeah. So yeah, I started with fg prime. Okay, good. So integral fg prime dx a to b is equal to fg a to b minus integral fg prime. Good. A to b. So yeah, we've got the boundary, and we've got the integral. So it's really the same. It's absolutely just the fundamental theorem with the product rule. So what we want to do is apply this to some of those laws that I had just erased here. And I'll do one of them. So for our integration by parts, I'm going to use the product rule. This integration by parts. Make sure I'm with my numbering scheme here. Yeah, so we're going to use one of those product rules. So this was, of course, a product rule. Using the product rule of divergence of f times a. Very good. So divergence of the scalar times a vector equals f div a minus a dot grad. So should be plus, yeah. F divergence a plus a dot gradient of f. Okay. So that's a product rule, and we're just going to integrate both sides over volume and see what happens. What's going to happen is exactly what happened here. So we integrate divergence of f(a) d volume over a volume equals integral f div a d volume plus integral a dot grad f d volume over a volume. get is the boundary term here by using Gauss's integral theorem. So now we have integral boundary of the volume f a dot n hat the area, and these two volume integrals we're going to keep the same. So finally we're just going to rearrange them to make it look like this. So it'll be the function times its derivative and so forth. So right underneath here, I'll write this one out. So we will have integral a dot gradient, a dot gradient f the volume is equal to boundary term f a n hat the area minus f divergence a the volume. So there are other integration by parts formulas. Let's put a box around this one that you can do for the other differential product rules and using the other Stokes' theorem, for instance. But yeah, you see how they just fall into your lap. So we have that, and that would be my discussion of integration by parts. If we weren't doing this so rapidly, we'd have all kinds of interesting examples, but okay, great. So what's ninth on my list here? These two I'm going to do quickly now. Okay, so that was 8, so we'll go to 9 here. So 9th, one needs a discussion of the delta function. So I'll just remind you of the delta functions, Dirac delta function. You can start with something like this. Say you have negative 1 over n, and n here, and this function, I'm just going to draw a spike. So the area under that spike is exactly 1. Okay. So let delta n of x be defined like that. So 1/2 times 2 over n. Good. So the area there under this spike, and then you integrate it, or you define integral, then delta n of x dx, I'm just going to go from minus infinity to plus infinity, is equal to 1. And in particular, in the limit as n goes to infinity, it's equal to 1. So I'll just write note the limit n goes to infinity. What that allows us to do is formally define a delta function like this. We have an f of x delta x minus a dx over the entire real axis for simplicity. And because this delta function is one of these spikes that's infinitely thin with an area of 1, this just gives us equals f of a. So in one dimension, this has a lot of uses, over which we could do an entire little section. But we also need the delta function in 3 dimensions. Okay. So I'm going to go ahead and erase this now. So the delta function in 3 dimensions. There we would have integral delta of r. Here, let's go ahead and do this. Integral f of r delta r minus a d volume, say over all of space. No, but the same type of construction as this. This would just give us f evaluated at that point A. So we've got the same spike behavior here, infinitely narrow, infinitely high, with that property in 3 dimensions. So we need some of these in order to operate with all of these laws that we've been putting together right now. So I'm just going to give a couple of examples. So I'm going to give an example. And by the way, we call this delta cubed, right? That's what we have here. So here's one example. This delta cubed of r is equal to, we got a factor of 4 pi here, 1 over 4 pi, 1 over 4 pi divergence of r over r cubed. Okay. So that's an example of a delta function. And in fact, what you can do is prove this using Gauss's theorem. So let's even go ahead and do that. So now we have integral 1 over 4 pi divergence of r over r cubed d volume over all of space equals 1 over 4 pi. Now we'll use Gauss's theorem, so we would have the integral, oops, we got to do a sphere. We're going to do sphere capital R. Okay, and then we'll let R go to infinity. So what do we have here? The boundary of the sphere, R, and since there's our vector field, we're talking about R over R cubed dot n hat d area. Got 1 over 4 pi. But this n hat for a sphere is just going to be R. Should I do that? I'll do it. So yeah, we've got 1 over 4 pi, and that integral here, d r sub sphere, okay, it's a sphere. Yeah, so we have r over r cubed, but that unit vector on the surface of the sphere is just r over r like that. So what is that? The area, that is integral, got 1 over 4 pi, r squared over r to the 4th. Okay. And when you integrate up over the area of that sphere, you get 4 pi r squared. I'm just going to say it now, you guys can fill that in. You know, you've got r squared over r to the 4th, and you're on the sphere of radius r, and then the area is 4 pi r squared. So that's going to, r squared over r squared is going to cancel that. You're going to get that 4 pi, cancel that 4 pi. So that does equal 1. So this is an example of a delta function in 3 dimensions. And you'll notice it's a divergence of some very typical central field. And so, actually I gotta consult the clock here, see how we're doing. Fine. So what this leads us to, it's a useful tool. I'm also going to say also, since this is minus the gradient of 1 over r, okay, this here, this argument, minus the gradient of 1 over r, scalar over r, then we also get del squared, in other words, div grad, del squared 1 over r is equal to minus 4 pi times that same delta function. Okay. Now the point with having a couple of delta functions like this is that you can insert them or you can find them in an integral, the integration problem that you're doing, and that immediately delivers the integral to you. Okay. And they're common operators, and they're common operations on common expressions. Good, so we have this expression and this expression for delta functions. Okay. So what follows, and let's keep our scheme going here, delta functions were 9, so here we are at 10. What follows here is the Helmholtz theorem. So the Helmholtz theorem is that a vector field, so a vector, I'll just put it this way, a vector can be expressed as the sum of a gradient and a curl. Okay, so a vector f can be expressed as f is equal to minus gradient of a scalar plus the curl of some vector. Okay. So that's a scalar function of position, and that's the curl of a vector. So this is the Helmholtz theorem, and if you have a lot of time and interest, you can take all of the steps that we've done so far, and you'll see they go into constructing this theorem. Okay, so that's why I have everything in this order. So the proof is a few pages, and if you're Helmholtz, you could actually invent it. But it's actually an interesting construction, makes use of everything we have here, or a lot of what we have here. In particular, these integrations by parts, these delta functions play a role. So that's why we would have all of this in the list. This Helmholtz theorem is very important. Okay. A vector field can be expressed as gradient of a scalar plus the curl of a vector. And then, you'll have curl, you'll have those relations, divergence and curl, that you can apply to this to isolate it as one part or the other, depending on whether it's a curl-free or a divergence-free field. So yeah, this is used a lot, especially in theoretical constructions, where you have a vector and then you say, well, I can express it as the gradient of a scalar and the curl of a vector, and you move on from there. So all of these, like I said, all these ingredients go into the construction of this, and you can find that construction in a good book, and it's interesting. So I recommend it to everybody. what do I have 11th on my list? 11th on my list, after you have all of these ingredients, you can move to curvilinear coordinates, which we're not going to do now. Everything gets very complicated seemingly in curvilinear coordinates, but say you have your Euler equation and you want to solve it in a certain geometry, okay? You know, cylindrical coordinates, etc. Then you're going to have to transform all of your derivative expressions, okay? Curvilinear coordinates and differential operators. That's what, so that's something we would deal with when we get there. As long as we're just doing the theoretical aspect of some simpler problems, we want to always use Cartesian coordinates as long as we can. Okay, so that's a fast run through vectors. Okay, excellent. And I can even, having done all this, or mentioned all these things, really, just mentioned them, talk a bit about the thermodynamics that we need as well. Okay, great. Good. This will also be a truncated presentation, but still we'll have the essentials here. So let's see. So now let's just call this thermodynamics. Don't actually need that much. But we have those straight line quantities in our Euler equation and other equations. So let's see here. We'll first consider a fluid sample. And we'll have energy, pressure, entropy, etc. So energy E, entropy S, volume V, temperature T, pressure P. Now I also have some chemical potentials in here, but we're going to say no chemical reactions going on. So we can skip that. No chemical reactions. So then we would have our fundamental relation here, T ds minus P dV, okay, for the energy. Next, though, we're going to go to density, so we'll divide by volume on these things. Okay. So next, fluid element with mass delta M, so we're looking at a small fluid element. Internal energy per unit mass, lowercase u, entropy per unit mass, lowercase s, so I gotta write these down. Entropy per unit mass, lowercase s, those are the ones we're gonna use, along with the densities that we have in the fluid mechanics. And then volume per unit mass is going to be equal to 1 over the density. So in that case, this here will transform into du equals t d lowercase s minus p d 1 over rho. Okay. That's the inverse there, right? P d 1 over rho. So good. These are the quantities we're working with. And as far as this TDS goes, remember you had delta Q equals delta S you had delta S is equal to Q over T. Delta Q over T. That was in your elementary thermo where you had the change of entropy, and this was an energy flowing in to an object over T. So if you just cross multiply this, you'll see your TDS, that's the change of internal energy. That's the thermal part right here. And then subtract off the work part, EdV. Okay, so that's the change in internal energy involving the entropy. Okay. So yeah, I just said it. Might want to put that in, right? That's the internal thermal energy, and then there's your work done on the sample. Okay, so that's still this. Okay. So now we're going to introduce a different thermodynamic potential and do a transformation. So next, we'll introduce the enthalpy. And we're going to use capital H E plus P times V, and then lowercase h will be U plus P divided by rho. And now we'll take the total differential of this and this is essentially a Legendre transformation. So then dH is equal to du plus dP divided by rho plus P d 1 over rho. And this here is the T ds that we just have up there minus P d 1 over rho plus dP over rho plus P d 1 over rho. And you see we get that cancellation. And there is our new relation here, dH equals T ds plus dP divided by rho. So this here we can use now to transform our Euler equation into a more convenient form. Okay. And I think that's what we'll end with here. Let's see, I have a couple of comments here. I changed the name of some of these letters, but I'm going to stick with what we have on the board now. Or actually, so next, I am going to change the letter. Use W equals H enthalpy, simply because I'm working with the book by Landau. Okay, so Landau uses that, segueing back into Landau, and then we'll have the following situation now. So we're just going to use W, so I'll even write it down. dW equals TPS plus TP divided by rho. So now, okay, we'll put a box around here too. Now we're going to have to remember something about our original equations of motion. Now, recall, we had, and you know, I'm going to write all of them down just so they're here. We had d rho dt plus divergence of rho v, just to show you how these come up. And we had the Euler dv dt v dot grad v equals -1 over rho grad p. We'll leave the g out for now. And then we had, this was ds dt entropy, which we have now in front of us, okay, ds dt plus v dot grad s equals 0. So the condition, let's go ahead and showcase these, in particular this last one. Okay. So the condition that we have here, okay, for energy not being dissipated, is that this ds itself, or ds dt, but the ds then can be thought of as being equal to 0. Okay. So in our Euler equation, or in our fluid equations, or in fact, let's say in our ideal fluid equations, that's what we've been doing here. We can think of these as the frictionless fluid equations. We have ds is equal to 0. Okay. We have ds is equal to 0, and I'll go ahead and erase over here. So if we want to talk, so if ds is equal to 0, we just have the dw dp over rho, and from this, we thus have the following. We have, you know, we just convert this differential, we take the derivative, so we have gradient of w is equal to gradient p divided by rho. Where this is now the enthalpy density. And that allows us to go into here. So now Euler equation can be written as dv dt plus v dot gradient applied to v equals minus gradient of w here. Okay, it seems like a lot of work just for that small change in the differential equation, but it's going to allow us to use some vector identities without always insisting that the density be constant, okay? Because we want these equations to be as general as possible. So that's where I'm going to stop today. We did the thermo. This is basically what we got out of it, being able to replace gradient P over rho by just the gradient of an enthalpy. And, you know, we can regain this immediately with constant density. So we can go back and forth, but this is going to be more general. And for example, you know, we'll be able to use our curl grad. Curl grad equals 0. If we apply the curl to, say, an entire equation, then boom, that gets wiped out. Whereas, you know, that'll vanish. Whereas you couldn't say curl of gradient P over rho vanishes in the same way. Okay? So that's not a bad place to be. So next time we'll actually start with this result and make use of some of the vector quantities that we just studied today. Good, so that'll end it for today. See you guys next time.